right, so we left off talking about molarity and molality, and now we want to practice using them in context. So here's an example of molarity. A saline, that just means salt, solution contains 0.015 moles of sodium chloride and 100 milliliters of solution. So the first thing we do to calculate the molarity of the solution is write down the formula. So molarity is equal to moles of solute divided by volume of solution. So we plug in our moles, 0.015 moles divided by 0.1 liters, and that gives us 0.15 molarity NaCl. Molality is a little bit different. So we're going to talk about a solution made with 0.03 moles of potassium iodide dissolved in 500 grams of solvent. So we need to remember that for molality, we have moles of solute divided by mass of solvent in kilograms. So we'll have to take our 500 grams into kilograms. We can do that by just dividing by 1,000. So that means we have 0.5 kilograms of solvent. So we can plug in our numbers. Molality equals 0.03 moles divided by 0.5 kilograms, which gives us 0.06 molal potassium iodide. There are other ways to express solutions as well, and one of those is percent by mass. So in this case, we express the concentration of a solution as grams of solute in grams of solution. So you would basically take your solvent, set it to the side, find the mass of your solute, dissolve your solute in your solvent, and then find the mass of the solution. You can also do percent by volume. So the concentration of a solution is expressed as the volume of solute out of the volume of the solution. So this would be a case where you're mixing two liquids, and that's where percent volume comes in really, really handy, is if you're trying to mix two liquids. So if you're trying to dissolve, alcohol in water to dilute it, or acetone in water to dilute it, that's when a percent by volume is really helpful. So equation for that, percent by mass, is mass of solute divided by mass of solution times 100. And percent by volume is the same, but with volume. So volume of solute divided by volume of solution times 100. All right, so now let's look at an example of each of these. A percent by mass example is what is the percent by mass of 6 grams of sodium nitrate in 50 grams of water. So we recall our formula, mass of solute divided by mass of solution. It's really tempting to just use 6 grams of sodium nitrate divided by 50 grams of water, but that would be mass of solute divided by mass of solvent. If we want the mass of the solution, we're going to have to add the mass of sodium nitrate to the mass of the water. So it actually would look like this. 6 grams of sodium nitrate divided by 56 grams of solution. So I'm accounting for the solute and the solvent when I'm talking about the solution. And then I would multiply by 100. That gives me 10.71% sodium nitrate by mass. Very similar process with percent by volume. A solution is made by mixing 7.5 liters of 0.25 molar sodium chloride with 12 liters of 3.3 molar potassium hydroxide. What's the percent by volume of each component? So in this case, it seems like a little overwhelming because we have those molarities included in there, but the molarities actually don't matter because we just want to know the percent by volume of each component. So we'll just ignore the molarity for now, and we'll address it in a minute. We're going to take our equation. We got the volume of the solute and then the volume of the solution. Again, for the volume of the total solution, we need to add the volume of the first solution and the volume of the second solution to find the volume of the total solution that we're making. So we would have 7.5 plus 12 liters gives us 19.5 liters of solution total. Now that we've thought about that, we can start to work out the percent by volume of the sodium chloride component and the percent by volume of the potassium hydroxide component. So the percent by volume for sodium chloride, we would have the 7.5 liters of sodium chloride divided by the 19.5 liters of the whole solution times 100. And so then we could say we have a solution that's 38.46% 0.25 molar sodium chloride. So that's where the molarity comes back in. We're saying about 38.5% of this solution is made out of 0.25 molar sodium chloride. We'll do the same thing for the potassium hydroxide. There's 12 liters of potassium hydroxide divided by 19.5 liters of total solution times the 100 gives us 61.54%, 3.3 molar potassium hydroxide. So over half of the solution contains 3.3 molar potassium hydroxide. Something I'd like to point out to you at this particular juncture is that these two percentages add up to 100. That makes sense because we're adding two solutions to make one solution, which means that they should account for 100% of the final solution. All right, the last kind of bit that I want us to consider is what happens if you take a solution and you add more water to it. And most of us kind of have an intrinsic feel for this, right? If I take your Kool-Aid or your Gatorade or your apple juice or whatever, and I dump a bunch of extra water into it, what happens? Right? It becomes kind of less flavorful, and the flavor is less concentrated, or it tastes diluted. And that's because you have less solute per volume of solvent. The concentration is lower. And there's a way for us to easily calculate the exact effect of this. So if you add that pitcher of water to the Kool-Aid's not going to taste as strong. It's not going to be as sweet. And we would say it's less concentrated. We might say it's diluted. We might say it tastes bad. So dilution is the process of adding more solvent to a solution, lowering the concentration without changing the number of moles of solute. So we're not changing the amount of sugar in the pitcher. We're just increasing how much water is in there. And so this is the most important idea behind dilution, is that the moles of solute stay the same. If there's 5 moles before dilution, there's 5 moles after dilution. And that's where this whole calculation comes from. So before dilution, you might have 6 particles in a square inch, but after dilution, you might only have 3. Okay, so you can see here that the volume doubled, and so the concentration got cut in half, and that type of relationship is always going to be true. So we can actually use a formula, which is the molarity of the first solution times the volume of the first solution has to be equal to the molarity of the second solution times the volume of the second solution. So that's saying if you have a molarity and you increase the volume, the molarity has to decrease in order for those things to stay equal. because we're not changing the number of moles. For example, what volume of a 2.0 molar solution should be used to make 500 milliliters of a 1 molar solution? So we got our formula, M1V1 equals M2V2. Plug it in, 2 molars of one solution times volume 1, because we don't know how much we're going to use. We know we want to make 500 milliliters, which is 0.5 liters, and we know we want it to be 1 molar. So we'll plug all those guys in, and we're going to solve for V1. So we end up dividing 0.5 by 2 molar, gives us 0.25 liters. So we would take 0.25 liters of solution 1, and we would put it into a new container, excuse me, and then we would fill it with water until it got to 0.5 liters, because the final solution that we want to have is 0.5 liters. And this type of process is something that we actually do a lot in chemistry, is diluting things to get them to the concentration that we want. So, very useful skill later on. The last piece I want to talk about is how stoichiometry interacts with solutions and solution chemistry. So, for example, how many grams of solute are required to make a 6.21 liter solution of 0.76 molar copper 2 sulfate? Okay, so a couple pieces here. First thing is I need to find moles. I have a molarity, I have a volume, I'm going to find moles. Then for moles, I can use the molar mass to find grams. We're pretty experienced with that. Okay, so solve for moles, 0.76 molarity equals moles times the volume. That gives us 0.12 moles of copper sulfate. Plug 0.12 moles copper sulfate into a little baby stoich line. We wind up with 19.15 grams of copper 2 sulfate. And that's what we would need to add to our solution. Another example actually requires us to think a little bit about a chemical reaction. So first we're going to write and balance our chemical equation. So we have aqueous sodium carbonate plus calcium chloride gives us sodium chloride and calcium carbonate. And so if we start with a 1.75 liters of a 0.07 molar solution, and then we combine it with 1.25 liters of a 0.05 molar calcium chloride solution, we want to know how much calcium carbonate we could make. So we're going to use the molarity equation to find moles of each reactant. So 0.07 moles, or molarity, equals moles times 1.75 liters. For calcium chloride, 0.05 molarity equals moles times 1.25 liters. So there's my moles. In this case, the moles are the same, but this is a limiting reactant step, right? We're looking to make sure there's not a limiting reactant. In this case, there's no limiting reactant, but we had to check just to make sure. So now that we've identified our limiting reactant as not really existing, right? We had to use our balanced chemical equation, to say our 1-to-1 mole ratio. So there's no difference between our two reactants. Now we can use our 0.04 moles of calcium carbonate to calculate our mass of calcium carbonate. And so we have 0.4 grams. Okay, that is it, y'all. You're going to have some practice problems to practice your solution stoich. Remember, this is for us to feel like we've been exposed to gases and solution chemistry, even though we didn't get to go into detail because of the social distancing situation. But I did really want to introduce you to this so that if you go on to take chemistry again, it's familiar to you, and somewhere in the back of your brain, you'll hear me, making goofy videos or whatever. Anyway, I love you guys.